Hello, everyone. Welcome to my talk today. My name is Sasha Loewen. I am a PhD candidate at Montana State University. My advisor is Dr. Bruce Maxwell, and I'm going to tell you today about my research with precision seeding rates in organic grain systems. So, getting right into it, my research question is whether we can use precision seeding rates to enable better management in organic systems. We're looking at optimizing green manure seeding rates, as well as cash crop seeding rates, to maximize farmer net return and hopefully manage weeds as well. So, little quick introduction background here. My lab mates and I have recently published a paper called Precision Agroecology, in which we talk about what we see as two competing paradigms in agriculture today: the production-oriented paradigm, which is driven by technology and yields, and the ecologically oriented paradigm, which is driven by ecological management. And we imagine a world in which precision technology can actually take those agroecological principles and enable the optimum management situation in which we fuse ecological farming methods with modern technology. To do that, we see on-farm experimentation as being the best method to deploy that. On-farm experimentation is becoming more and more popular. It's enabled by the ease of which data is able to be acquired on machinery and from satellites in today's information age. Using that massive amount of data is now becoming easier and easier to experiment across a farm or across a field, generate prescription maps that are specific to that field or farm. And so on-farm experimentation is a perfect way to implement precision tools to enable better ecological management on farms. So on-farm experimentation begins with engaging the farmer, acquiring as much data as possible, analyzing, then getting back with the farmer and discussing the results and layering the newfound information from this data analysis on top of what the farmer innately already knows from often managing that farm for decades or generations. So how does on-farm experimentation work? We always begin by generating a prescription map with some sort of experimental design laid out across it. And this is for any input that the farmer would choose. In my situation, I'm working with organic farmers. And so we are laying out experiments in which the seeding rates of both cover crops and cash crops are varied to determine optimums. And so we begin with that experimental design randomized across the entire field so that we can learn about the entire field. We collect as much data as we possibly can from satellite information, from equipment, seeders and combines and so on, the yield from the combine mounted yield monitor, of course, being a crucial output. And then we come up with an analysis. We've tried a number of different analysis techniques, but currently random forest is the model that we are finding has the greatest efficiency and the most accuracy for our purposes. Based on that model, we then come up with what the optimized seeding rates would be for a maximized net return for the farmer. From that, we can then generate a new prescription for the following season that farmer plants that crop. And that prescription then enables better optimization across the field, but we also layer on top of that continued experimental rates so that the farmer and we can understand the effects of these seeding rates over both space and time. So we have a number of experiments laid out across the Great Plains, mostly in Montana, but also back home where I'm from in Manitoba. But today I'm going to focus on just one example here from the Norgard farm, where the farmer planted a varied rate of pea in 2020, plowed it in as a nitrogen source for the following cash crop, which was winter wheat, which they planted that fall, and they harvested that crop this past summer in 2021. So here's just a drone shot of that field where the farmer planted these pea and wheat varied rates. And you can see already, this is a midsummer shot of the wheat. You can see that the variation across the field with both the dark and the light. So just to highlight what the field looks like for mapping purposes, The pea seeding rate, you can see the different green bands represent the different levels of pea seeding rates that the farmer put in across the field, from as low as 70 pounds an acre to as high as 130. Similarly, they planted wheat across the entire field in randomized strips, all the way from as low as 49 pounds up to 91 pounds per acre. And I've put elevation on here as well, so you can start to get a sense for the variation across the field, higher in the southwest and lower areas in the north and the east. And then from that information, of course, the farmer gets an actual yield, and we generated an approximate net return based on seed costs, fixed costs, and the approximate price received for winter wheat this past season. So all of that information plus a number of satellite indices go into our random forest model. So in the top, you can see what the random forest model looked like. I've shown a few more maps here in the top row of maps, highlighting some of the important variables that go into that model. You can see water content and clay content and pH are unique in that they are relatively new satellite indices with relatively low quality of or scale. So the NDVI, for example, is at 10 by 10 meter grid cell, and I think these other two are more along the lines of 100 meter by 100 meter. So we get less information, but it does still go into our model because it is still enabling better prediction. And we're hoping that moving forward, there will be better and better resolution of these variables from satellites so that these models can be improved. Anyway, all of these things go into our random forest model to generate predictions that we are then able to come up with optimum seeding rates. So I want to highlight a few of the optimization scenarios that we go through. We played around with a number of different ideas, but the basic three are, well, the first one is the simple farmer chosen rates. So this is what a farmer would have done in a normal year without any variable rate technology or without any experimentation. Plant 100 pounds of peas, 70 pounds of wheat, and this is what our model predicts they would have received. That's sort of a baseline then to compare to better optimization strategies. We then use our model to predict what the optimum average would be. So if the farmer wanted to do no variable rate application at all, but simply learn from the experiment what the best optimum average would be across the entire field, given the same weather conditions, we actually saw very low rates, actually the lowest rates that were experimented with as the optimum average. This is likely highlighting the drought situation that occurred over the past year and highlighting that lower densities would have done better. You can actually see, though, that the model is predicting that compared to the previous one where we got 51.64, we've now actually declined by 0.1 bushel. And that's, but at the same time, the net return has gone up quite a bit. And so basically the model is suggesting that we can save seeding rates since those higher densities weren't contributing any, they were hardly contributing to yield. And finally, the what we usually hypothesize as being the best model is the variable rate model across the field. So here you can see varied rates of pea in the green, varied rates of the wheat in the orange, and how we could layer those across the field to produce the optimum the maximized net return. And so there we can start to get a sense for where the highest plant densities are suggested by the model across the field, and that contributes to both the highest yield and the highest net return in this instance. So these are three situations we lay out for the farmer. Then to get a sense for some of the probability of which method would be best, we in this instance we only have the 2 years of data of the entire experiment of the wheat and the pea, but to start to get a sense for what the variation looks like economically, we do have many years of data going back in this instance to 2000. So we have 21 years of economic data, which we can punch in. So the fixed costs vary, the seeding costs vary, and the price received varies. And we can say, okay, which of these situations would be best for you as a farmer, given that economic variation. And in the first box plot here, we see the change from the base scenario, the first row of maps here, to the varied rate technology scenario. And you can see we get an improvement of almost $8 per acre, and that 100% of the time that outcompetes the base average the farmer would have chosen. In the second box plot, we see the varied rate technology, the bottom row again, compared to the optimum single rate. Here it's much closer. Here the varied rate only competes it by about $1, and it only competes it about 2 out of 3 times, 67% of the time. And so based on that information, the farmer can then start to make educated decisions on which style of management they would like to deploy, whether they want to invest in better precision ag technology, and so on. And over time, as we collect more data from these fields, we can also then start to layer in varied weather data and so on, so that we get a sense for the temporal variation across these fields. Okay, then finally, just to begin finishing up here, we also want to explore, so we explore those economic situations with the farmers. We also want to explore what some of the drivers are. So in the basic sense, we put all these information into a random forest model, come up with a prediction, but we don't want it to just be a black box. So we spend time looking at these maps, seeing where things layer on with how they understand their own field. And then we can also show variable importance graphs, which really highlight where the variation is coming from in explaining yield outputs. And so along this y-axis on this variable importance graph, it's showing everything to the right explains more variation. And so elevation and NDVI are both very high on this map, which is kind of nice to see since those are so readily available metrics and freely available. But all that is to say, we spend time exploring these different driver variations with the collaborators that we're working with. So in the future, moving forward, we are developing software that the farmer can use, any researcher or agronomist can use to design these experiments and analyze them. Currently, we have a field prescription map generator up online. Feel free to check it out. All you need to put in is a boundary layer, and from there you can decide whether to layer over previous yields or not, to have it completely random, to say what your seeding rates are you would like to vary over, or any input of your choice. I think it's often set up for fertilizer as a default for the conventional farmers. But this process can be conducted then easily and relatively automated as well. So that's kind of the goal from this project. So that's what we're working on right now, is generating that free open source software. So just to summarize, we are trying to enable precision organic agriculture, that is organic agriculture that harnesses precision technologies to enable optimized cash and cover crop and cash crops for optimized net returns for the farmer. And moving forward, we're going to continue working with these farmers to explore how this varies over time and generate an open source software application so that hopefully anyone can conduct these experiments on their own. So thank you to my committee, my lab mates, and my collaborators. And yeah, thank you for listening. And please feel free to email me any questions. Thank you so much.